little bit about mass spectroscopy. Yeah, so I have a schematic of a mass spectrometer drawn here. These are very important instruments in the chemistry field. You'll see why as we describe it. There's basically 5 parts to this. It's where you inject the sample here and the sample gets vaporized. We're actually going to inject some copper. Okay, you see the penny there? Then what happens here is the copper gaseous atoms are going to get ionized. So there's a cathode ray tube set up here. There's electrons flowing, and they'll knock an electron out of a copper atom and make it have a positive charge. Okay, and we're going to assume that only one electron gets knocked out. So all the ions that are formed here will be +1. All right, and then these +1 ions are going to be accelerated through this little slit. So this is negative. This will have a negative charge. It'll be accelerated, and it'll go into this magnetic field. All right, and we'll see what happens with that in a little bit. And then there's a detector here that can detect the charged ions. All right. So 5 different parts to this mass spectrometer. Let's inject some copper. Here we go. So we're going to inject some copper. So think about all the copper atoms that make up that penny. We're going to inject these guys. So we're going to have a bunch of copper atoms. And then here, they're going to turn into ions. Okay, so let's just assume that the copper 1 ion is formed. They're going to get accelerated by this ion accelerator into this magnetic field. Now, what we're going to see is that one copper ion is going to get deflected just a little bit, but another copper ion may get deflected a little bit more and hit at a different spot in the detector. All right, so this is a copper ion here. This is the path the copper ions are taking. And this one here is not getting as deflected as this one. So why is that? Why would one get deflected more than the other? So these copper ions, they're going pretty fast. They're going with a constant velocity. Inertia just says they just want to keep going in a straight line. The magnetic field is able to deflect them. Why would one get deflected more than the other? Well, it has to do with, 2 things. Mass, and they're going the same speed, so momentum. And you physics people probably, you guys know that momentum is equal to mass times velocity. They both have the same velocity, so the mass is going to be the key here. The more mass, the more momentum. Which do you think has the more momentum? Which one has the more inertia? Which one's the one that gets deflected the least, right? So think about a car going around a curve or a semi truck going around a curve. Which is more likely, if going at the same speed, to navigate that curve? Right, the lighter one, right? The one with less momentum. You often see signs when you're exiting highways for trucks to beware that they could tip over. All right, so this implies that there's different types of copper atoms that have different masses. So of course, those are isotopes, and the 2 isotopes of copper are copper 63 and copper 65, okay? All right, the 65, of course, would be this one. So the 65 would hit the detector here. The 63 would get deflected more. It would hit the detector here. So this is a little graph, a spectra of what would be generated here at the detector. So let's imagine all these copper ions going through this mass spec, and let's keep track of these two ions. So one's at 63, others at 65. All right. So here we go. All right. Let's say, all right, 63. Some 63's hitting. Oh, there's a 65 getting hit. All right, more 63. Okay, some 65. See what I'm doing here? There's more. Which has a greater abundance? The 63, yes. All right, here we go. And here comes more 63. There's some 65s. 63, 65, 63, 65, 63. Okay, all right. So this is a mass spec of copper. It clearly shows that the percent abundance of copper 63 is greater than 65. We can actually determine the atomic mass of copper, what's on the periodic table, the atomic mass of copper, using a spectra like this. You'll be asked to do this in some problems. So what we do is we measure this height. This is, let's say this is 7 centimeters, and this is 3 centimeters. So to figure out the percent abundance of copper 63, remember you can put the mass number there too. Mass number there or there. Okay, so what we do is take 7 centimeters. Now this is going to be important. What we want to do is we're going to divide this by the total heights of the peaks. So we're going to take 7 centimeters plus the 3. So it's going to be 7 divided by 10, and that'll give us 70%. So the percent abundance, this is an approximation. I think it's actually more like a little less than 70%. So the percent abundance of copper 63 is 70. Of course, then copper 65 would have a percent abundance of 30%. Okay? There's only 2 isotopes of copper. Only 2 naturally occurring isotopes, because there are some man-made isotopes of copper. Okay. All right, so we'll do one more thing, one more calculation. Let's use these to figure out the percent of the atomic mass, what's given on the periodic table. So what we can do is take 0.7 times the 63, the mass, add it to 0.3, we'll change the percentage to decimal, multiply by the mass, same thing here. And we'll do this arithmetic. And I did it earlier, but just let me use my calculator for a second. 0.7 times 63 is 44.1, remember that? 44.1. And 0.3 times 65 is 19.5, so let's add those up. It's 63.6 or 64. The actual atomic mass is 63.55, but I approximated those heights. These percentages are a little off, so that's how we do it. Hey, so let's review a couple things. So we inject the sample, it gets vaporized. So these are gaseous atoms now. The atoms are ionized, so there's enough energy to knock off an electron. We're assuming just one electron is knocked off. It's accelerated through this ion accelerator into this magnetic field. This is the key portion of this. So the one that gets deflected the less is the heavier. In this case, it's the 65, and the 63 gets deflected a little bit more. Okay? Detector's here, and then this is the readout from the detector. In this case, you can see that there's a lot more 63 that hits the detector than the 65, showing it's more abundant. That's why the atomic mass is closer to 63. I think that's all we're going to do for that. So, of course, you guys know about isotopes. Just a reminder, atomic number for copper is 29. Let's say we have a +1 here. So we know that's 29 protons. It's +1, so it has 28 electrons. If we subtract the mass number and atomic number, we get the number of neutrons. All right? I guess we didn't mention that. The reason they have different masses is because they have different number of neutrons, all right? This is 2 more neutrons than the 63. I think there's something else. Oh. Hey, maybe you noticed that. That's the mass to charge ratio. Z is the charge. So what we're doing here is just assuming that the Z is +1. That's pretty common. So the mass to charge ratio is just simply the mass. If back here, if these guys, if this is +2, it's going to get deflected more. If the charge is greater, it's going to get deflected more by the magnetic field. So we're assuming here that all these ions are +1. So then we can just look at how the mass affects the deflection. All right, that's it. Thanks.